Welcome to Animal Uncovered, the podcast where we explore the most unbelievable life cycles in the natural world. From the moment life begins to the moment it ends, nothing is as simple as it seems. Somewhere in the darkness of a Costa Rican cattle ranch, the night has reached its deepest hour. It is 2 a.m, and the air carries the warm, grassy breath of a dozen sleeping cows. They stand or lie in the open field, their breathing slow and rhythmic. Their minds, if we can call them that, to drift in whatever passes for bovine dreams. They are enormous animals, each one weighing the better part of 1,000 pounds, utterly unmoved by the world around them. Above them, something moves. It doesn't fly in the way you might imagine. Not the great swooping arcs of an owl, or the frantic, erratic flicker of a moth-chasing bat. This creature moves with a kind of controlled, deliberate intention. It circles once, then it drops, landing not on the animal's back, as folklore might suggest, but on the ground nearby, several feet away from the sleeping cow. And then it does something that no other warm-blooded creature on Earth does in quite the same way. It walks. Using its forelimbs, its wings folded back into something resembling arms, it moves across the grass with a bouncing, almost puppet-like gait. A motion so unusual, it took scientists years to fully understand it. It approaches the cow's leg. It tests the air with a nose so sensitive it can detect the heat rising from just beneath the surface of the skin. In less than a minute it has found its spot. A patch of thin skin near the ankle, where blood vessels run close to the surface. What happens next is almost surgical in its precision. The animal leans forward and makes an incision no larger than a pinprick. There is no pain. There is no reaction. The sleeping cow does not flinch, does not shift its weight, does not dream any differently than it did a moment before. And for the next 20 minutes the small dark creature laps at the wound, drawing a thin stream of blood, its saliva working constantly to keep that blood from clotting. It drinks perhaps 2 tablespoons, a volume that sounds trivial until you consider that it represents 30% of the bat's body weight, the equivalent of a 150-pound person drinking around 45 pounds of fluid in a single sitting. Then it is gone, back into the dark, back to the roost it shares with dozens of others, back to a colony defined not by hierarchy and dominance, but by something far more remarkable: generosity. The cow wakes in the morning with nothing more than a small, almost invisible wound and a very slight, unremarkable memory of the night. The bat, however, has just completed one of the most extraordinary feeding acts in the entire animal kingdom, and the story of how it came to do that, how a small furred winged mammal arrived at this precise and unlikely way of surviving, is one of the most fascinating evolutionary tales nature has ever told. Part 1. Why this animal matters. There are roughly 1,400 species of bat on this planet. They make up nearly a fifth of all mammal species. They navigate by sound, they pollinate rainforests, they consume billions of insects every night. Most of them are ecologically vital and by any reasonable measure beautiful in their own strange way. But of all the bats that have ever existed, only 3 species in the entire world feed exclusively on blood. 3 out of 1,400. Those 3 are the common vampire bat, the hairy-legged vampire bat, and the white-winged vampire bat. All 3 live exclusively in the Americas, from Mexico down through Central America and into South America and Trinidad. But it is the common vampire bat, Desmodus rotundus, that we are here to talk about today. Because of the 3, it is the one that has most completely surrendered every aspect of its biology to a life built around blood. It is, in a very real sense, the most specialized predator in the mammalian world, and yet it is also, as we will discover, one of the most socially sophisticated. The reputation of the vampire bat precedes it in ways that are rarely fair. When Bram Stoker wrote Dracula in 1897, he was drawing on centuries of Eastern European folklore about the undead, but the word vampire as applied to bats didn't enter the English language until European explorers returned from South America with stories of small, blood-feeding creatures they found genuinely unsettling. The mythology and the animal became entangled almost immediately, and the bat has been paying the price ever since. It is feared, misunderstood, persecuted and exterminated by the millions every year, by farmers who see it only as a vector of disease and a drain on their livestock. But strip away the mythology, and what you find is an animal of almost breathtaking elegance, a creature whose anatomy has been shaped by tens of millions of years of evolution into something so precisely fitted to its purpose that it borders on the miraculous. A mammal that has evolved anticoagulants in its saliva, heat-sensing organs in its nose, a kidney that can process enormous volumes of fluid mid-flight, and a social structure built around the sharing of food with hungry neighbours. An animal that, when studied carefully, reveals something profound about the nature of cooperation, survival, and the extraordinary lengths that life will go to in order to persist. The central question driving this episode is not, why does the vampire bat drink blood? That question, honestly, isn't very interesting. Lots of animals drink blood. Leeches, mosquitoes, lampreys, even some birds. The interesting question is deeper than that. The question is, how does an animal organize its entire existence, every cell, every organ, every social behavior, around a single, incredibly difficult-to-obtain resource? And what does that tell us about evolution, about cooperation, and about life itself? Part 2. Evolution and Origins. To understand the vampire bat, you have to go back roughly 60 million years to the forests of what would eventually become the Americas, where the first bats were beginning to appear. The earliest known bat, Onychonycterus phinei, discovered in a Wyoming fossil bed, dates to approximately 52 million years ago. It was already recognizably a bat, small, furred, with elongated finger bones supporting membranous wings, though it lacked the fully developed echolocation of most modern species and probably flew by sight as much as by sound. Bats as a group are thought to have evolved from small tree-dwelling insectivores, shrew-like creatures that perhaps began by gliding between branches to catch insects and gradually developed true-powered flight. This is the currently favoured hypothesis, though the exact path from ground-dweller to flyer remains one of the more actively debated questions in mammalian evolutionary biology. What matters for our story is that, by the time bats had spread across the Americas, they had diversified enormously into fruit eaters, insect hunters, fish catchers, nectar feeders, and eventually into something entirely new. The vampire bats belong to the family Philostomidae, the leaf-nosed bats, a group so diverse that it includes species eating everything from fruit to frogs to other bats. Within this family, the three vampire bat species form their own subfamily, the Desmodontinae. And here is where the timeline gets interesting. Molecular evidence suggests that the ancestor of all three vampire bat species made the transition to blood feeding somewhere between 26 and 30 million years ago. This was a gradual process, almost certainly passing through a stage in which the ancestor fed on ectoparasites, ticks and lice and biting insects, living on the skin of large vertebrates. In doing so, it would have occasionally nicked skin or lapped at wounds, and over enormous spans of time, natural selection would have quietly rewarded every individual that was little better at finding blood and processing it efficiently. This is a critical point. Blood feeding did not spring into existence fully formed. It crept in through the back door of parasite hunting. The bat was already on the body. It was already familiar with skin and warmth and the subtle cues of a living animal. The shift from eating parasites to drinking blood may have taken millions of years, but it was, in evolutionary terms, a short step, one reinforced by natural selection at every stage, because blood is, for all its difficulty to obtain, one of the most nutritionally consistent resources on Earth. Every drop of vertebrate blood carries a predictable payload of proteins, fats, and red blood cells rich in iron and oxygen. For an animal that could develop the right adaptations to access it, blood was a reliable resource that would never go out of season. The three modern species, Desmodus rotundus, Diemus youngi, and Diphila echidata, diverged from one another more recently and developed slightly different specializations. The white-winged and hairy-legged vampire bats tend to prefer bird hosts. Desmodus rotundus, the common vampire bat, developed a preference for mammalian blood. And when large domestic mammals arrived with European colonization, it found itself suddenly surrounded by an unprecedented abundance of large, slow-moving, easily accessible hosts. Its population exploded, and its relationship with human agriculture was transformed from one of occasional nuisance to something far more consequential. But we'll return to that. Part 3, the life cycle. Phase 1, birth. Somewhere deep inside a hollow tree, a limestone cave, or the dark recess of an old mine shaft, a female common vampire bat gives birth. She's hanging upside down as bats do, gripping the ceiling of the roost with her hind feet. The birth itself is short, lasting only a few minutes. The single pup, vampire bats almost always produce one at a time, emerges feet first, which is the reverse of most placental mammals, and the mother catches it with her wing membranes before it can fall. The pup is born relatively large and developmentally advanced compared to many other bat species. Its eyes are open or open within hours. Its incisors, those two sharp front teeth that will one day make precise incisions in the skin of mammals, are already present and functional, though in the early weeks they serve only to grip the mother's teat. It weighs roughly 6 grams at birth, about a third of its eventual adult weight. The colony around them might number anywhere from 20 to 100 individuals, though large aggregations of several hundred have been recorded. This is not a loose gathering of unrelated strangers. Vampire bat colonies are structured around long-term social relationships, primarily among females, who tend to remain in their natal colony for life. The males are more likely to disperse, though in many colonies a dominant male maintains a territory within or near the roost and fathers most of the pups born there. The pup being born right now was probably conceived roughly 7 months ago, with a gestation period that is unusually long for an animal of this size, a reflection of the heavy investment the mother makes in each offspring. Within hours of birth, the pup has latched onto its mother and begun nursing. Vampire bat milk is rich and calorie-dense, and for the first month of its life the pup is fed exclusively this way, clinging to its mother's chest as she makes her nightly foraging flights. This is a significant logistical challenge. A nursing female is carrying nearly half her body weight in offspring, making flight more energetically costly, even as she needs to drink enough blood to fuel both herself and her milk production. Phase 2, the juvenile phase. By the time the pup is 3 to 4 weeks old, it is beginning to eat solid food. or at least its version of solid food. It receives regurgitated blood from its mother, and this is where one of the vampire bat's most socially significant behaviors begins to take shape. Blood sharing, the voluntary regurgitation of blood from one bat to another, is not limited to mother and offspring. It is the cornerstone of the species' entire social architecture. And learning to participate in it begins, for this pup, at the very earliest stage of its life. At around 6 weeks of age, the pup's deciduous teeth begin to be replaced by its permanent dentition, and the characteristic razor-edged upper incisors are coming in. The bat is becoming, at least anatomically, something recognizable. Its facial features are developing the appearance that makes it so distinctive. The crumpled nose pad housing the infrared sensing pit organs, the large broad ears, the large eyes that collect as much light as possible, and the small, pug-nosed face that has been described, uncharitably but not inaccurately, as looking like a tiny, angry old man wearing a leather cape. At 2 months of age, the pup begins attempting to forage on its own. These early efforts are largely unsuccessful. Finding a suitable host, locating a good biting site, making a clean incision, and feeding without being detected or shaken off is a skill set that takes months to develop. Young bats often follow their mothers on foraging trips, observing her behavior and sometimes feeding at the same wound site after she's departed. This apprenticeship model, learning from watching an experienced adult, is unusual in the bat world and reflects how demanding and skill-dependent the vampire bat's feeding strategy actually is. The juvenile phase lasts approximately 9 months from birth to full independence, though mother-offspring bonds often persist well beyond this, playing out in the grooming relationships and food-sharing networks of the adult colony. Phase 3. Survival Challenges. Of all the challenges facing a young vampire bat, the most immediate and most frequently fatal is starvation. This requires some explanation, because at first glance it seems almost paradoxical. Cattle ranchers and wild mammals are not exactly scarce in tropical Latin America. How can an animal that feeds on something so abundant be so vulnerable to hunger? The answer lies in physiology. The vampire bat has a metabolic rate shaped by a diet of pure liquid. Its digestive system processes blood with remarkable efficiency. But the same efficiency means that its stomach empties quickly, and its energy reserves are thin. An adult vampire bat that fails to feed on any given night will have, by dawn, consumed roughly 90% of its overnight energy. A bat that fails to feed for 2 consecutive nights will die. This is not a slow deterioration. It is an abrupt metabolic cliff, and falling off it is something that happens quickly and regularly, especially to young, inexperienced foragers. In bad weather, heavy rain, cold snaps, or dense fog, finding and feeding from a host becomes significantly harder. Bats that have not yet mastered the full range of foraging skills are disproportionately likely to return to the roost empty on these nights, and this is precisely where the colony's food-sharing network becomes a survival system rather than a social nicety. When a well-fed bat returns to the roost and encounters a roostmate that is visibly hungry, and bats are very good at assessing one another's condition, using tactile signals and the subtle sounds of laboured breathing that come with hypoglycemia, it will regurgitate a portion of its blood meal for the hungry individual. This behaviour has been extensively documented by the biologist Gerald Wilkinson and others, and what makes it remarkable is not just that it happens, but who shares with whom. Sharing is not random. It is preferentially directed toward individuals with whom the donor has an established relationship, those who have shared in the past, those who are kin, those who groom together regularly. It is, in the clearest possible sense, reciprocal altruism. You help me tonight. I help you when your luck runs out. The bats are keeping track. For a juvenile bat still learning to forage reliably, this network is not a luxury. It is the difference between surviving the first year and not. Roughly 30 to 40% of young vampire bats die in their first year of life, most of them to starvation. Those that survive tend to be those who have successfully embedded themselves in these reciprocal food-sharing relationships, either through kin networks inherited from their mothers, or through the slow, careful cultivation of friendships, which requires persistent grooming, regular proximity, and demonstrated reliability. Phase 4. Maturity. A vampire bat typically reaches sexual maturity at around 9 months to 1 year of age, though females in the wild often don't reproduce until their second year. By this point, a surviving young bat has become something quite different from the helpless, clinging pup of the early months. It is a competent, socially integrated adult with a working knowledge of the local landscape, established relationships with a network of roost mates, and a refined set of sensory and physical tools that are among the most specialized in the mammal world. The bat's world at maturity is organized around 2 central activities: foraging and sociality. Every night, as darkness settles across the landscape, the colony begins to stir. Bats engage in mutual grooming, an activity that is simultaneously hygienic and social, reinforcing the bonds that underpin food sharing. The timing of departure varies. Some individuals leave early in the evening, others wait until later. The bats disperse from the roost individually or in small groups, each navigating by echolocation and spatial memory to hunting areas that may be several kilometers from the roost. Finding a host is only the beginning of the challenge. The bat must approach without being detected, land without disturbing the animal, locate a suitable feeding site, make a clean incision, and feed without interruption for 15 to 20 minutes. Each of these steps carries the risk of failure. A cow that stamps its foot or swings its tail can easily injure or dislodge a bat. A sleeping dog or pig that wakes suddenly becomes a genuine threat. The bat's ability to remain absolutely still, to minimize its weight on the host, and to detect the first signs of disturbance has been shaped by millions of years of exactly this kind of selective pressure. Phase 5. Reproduction. Mating in vampire bat colonies is a complex, politically freighted affair. In many colonies, a single adult male defends a roosting territory within the group and monopolizes mating access to the resident females. These males are typically large and experienced, and they invest considerably in maintaining their position through regular displays, occasional fights with competing males, and persistent grooming of the females whose proximity they guard. But the dynamics are never as simple as they first appear. Females are not passive participants. They choose. They groom males they prefer. They position themselves in the colony in ways that signal availability or avoidance. And molecular paternity studies have revealed that even in colonies with the dominant male, a significant proportion of pups are fathered by other males, a reflection of the female's agency within a social structure that males might imagine they control. Conception, as noted, leads to a gestation of approximately 7 months. The timing is not precisely seasonal in the way it is for temperate mammals. Vampire bats in the tropics can breed year-round. But there is evidence of some synchrony within colonies, with birth peaks tending to coincide with periods of relative prey abundance. A female can potentially give birth twice in a year, though annual reproduction is more typical. Over a lifetime of perhaps 6 to 8 years in the wild and up to 20 years in captivity, a successful female might raise a dozen or more pups to independence. The investment in each pup is substantial, and the mother's success as a forager directly determined whether that pup survives. A female who is herself well networked, who receives food shares on the nights she fails to feed, is better able to sustain milk production and carry her pup through its vulnerable early weeks. Reproductive success in the vampire bat's world is not simply a function of individual fitness. It is deeply entangled with social standing, with the quality of one's relationships, with one's reputation in the colony as a reliable food sharer. The most socially embedded females raise the most surviving offspring. Evolution, in this species, has discovered something remarkable. Generosity is heritable, not just culturally but consequentially. Those who give tend to receive, and those who receive tend to survive. Phase 6. Death and the aging colony member. Old age for a vampire bat brings gradual deterioration of the teeth, particularly those crucial upper incisors whose sharpness is the prerequisite for every successful feed. A bat with worn teeth has to work harder, takes longer, risks detection more often. It begins to fail on feeding nights with increasing frequency, and its dependence on the food-sharing network grows. Whether the network sustains aging individuals beyond their productive years has been an interesting area of recent research. The evidence suggests that long-standing social partners do continue to share with one another, even as one member of the pair becomes increasingly a recipient and less a donor, a reflection perhaps of bonds that have been built over years of reliable reciprocity and have accumulated a kind of social capital that outlasts any given period of productivity. Eventually the challenges accumulate. Failure to feed, predation by owls or snakes, disease, and the accumulated physiological costs of decades of high-intensity foraging bring the bat's life to its close. Its body, like all bodies, is returned to the ecosystem, and somewhere in the colony, a young bat that the old one may have fed on a desperate night years ago is hanging from the ceiling, grooming a neighbour, preparing for another night. Part 4. Biology and Adaptations. The anatomy of the vampire bat is a masterwork of evolutionary specialization, and it rewards close examination. Begin with the teeth. The upper incisors are triangular, laterally compressed and kept perpetually sharp by the way the upper and lower teeth meet. A self-sharpening mechanism not unlike that of a rodent's ever-growing incisors, though different in its mechanics. The canines are small and recessed. The cheek teeth are reduced and vestigial, because a bat that drinks only liquid has no use for grinding molars. The entire dental array has been redesigned around a single function, making a clean, painless cut. The painlessness of the bite deserves particular attention. The vampire bat's saliva contains at least 4 distinct anticoagulant compounds, the most famous of which is draculin, a glycoprotein that inhibits the coagulation factors in blood, preventing the wound from clotting while the bat feeds. A related compound, desmoteplis, has attracted serious medical attention as a potential treatment for stroke because it can dissolve blood clots in humans with remarkable specificity and relatively few side effects. This is one of those moments where studying a repulsive animal turns out to have direct medical benefits. Nature, as always, does not care about our aesthetic preferences. Beyond the anticoagulants, the saliva also contains compounds that dilate blood vessels near the wound site and suppress the pain response, which is why hosts so rarely react to the bite. The bat essentially anesthetizes the area before it cuts, draws the blood to the surface and keeps it flowing. It is, from a purely technical standpoint, one of the most elegant feeding systems in the natural world. The nose of the common vampire bat is equally extraordinary. That crumpled, leaf-shaped nasal pad contains a structure called the lateral nasal pit organ, a heat-sensing apparatus analogous to the pit organs of pit vipers, though independently evolved. This organ can detect the infrared radiation emitted by blood vessels close to the skin surface, allowing the bat to identify not just a suitable host, but the precise location on the host's body where blood flow is richest and skin is thinnest. It navigates to the ideal feeding site with a precision that no other bat possesses. The echolocation system of the vampire bat is less elaborate than that of many insectivorous bats, which makes sense given that it does not need to track fast-moving aerial prey. Its calls are low amplitude and broadband, more suited to navigating complex environments and locating large, stationary or slowly moving objects than to detecting moths in flight. But it supplements echolocation with acute hearing in the lower frequency ranges, which allows it to detect the sounds of large sleeping mammals, breathing, heartbeat, the sounds of movement, from considerable distances. A vampire bat can apparently identify individual cattle by their breathing sounds, a finding that has implications for understanding just how sophisticated and individualized its hunting strategy is. Its locomotion is famously unusual. The forelimbs, adapted for flight, have in the vampire bat also become tools for terrestrial movement. The wrist joint has been rotated in such a way that the bat can use its partially folded wings as front legs, and the large, robust thumbs serve as additional support points. This gives it a bounding, semi-quadrupedal gait on the ground that is unique among bats. Studies have shown that this locomotion is actually energetically efficient, allowing the bat to approach hosts from the ground with minimal vibration and noise. It can run at speeds comparable to a small rodent. It can jump straight up from a flat surface, an explosive upward leap that allows it to take flight without the running start that most bats require. This capacity is almost certainly an adaptation to foraging in open areas where a bat cannot simply drop from a height to begin flying. Its kidneys are worthy of separate discussion. Blood is approximately 70% water by volume. A bat that drinks the equivalent of 30% of its body weight in blood is taking on a massive fluid load, one that would be physiologically catastrophic if it couldn't be shed quickly. The vampire bat begins excreting this excess water almost immediately after feeding, even while still at the host. Its kidneys can process liquid at extraordinary rates, converting dilute urine from the plasma of the blood meal while retaining the valuable red blood cells and proteins. By the time the bat arrives back at the roost, a large portion of the water weight has already been eliminated. This adaptive urination is one of the lesser discussed but genuinely impressive aspects of the species' physiology. Finally, the bat's digestive system has been shaped to extract maximum value from blood's unusual nutritional profile. Blood is rich in protein and iron, but relatively low in carbohydrates. The bat's liver produces specialized enzymes for processing hemoglobin, and its intestinal lining is adapted to absorb amino acids and iron with unusual efficiency. The high iron intake, incidentally, creates an interesting byproduct. Vampire bats tend to have iron-rich blood themselves, which is detectable in the deep red-black colour of their internal organs. Part 5. Ecosystem Role. In the complex web of a tropical ecosystem, the vampire bat occupies a position that is easy to oversimplify. It is a parasite, specifically an ectoparasite in the loose sense, feeding on the exterior of the host's body. But its ecological role extends well beyond this simple characterization. In its natural, pre-colonial context, the common vampire bat fed primarily on large wild mammals, tapirs, peccaries, deer, capybaras, and various species of large rodents. These hosts were not significantly harmed by the feeding in most cases. A 2 tablespoon blood loss from a 200-pound tapir is genuinely trivial. The bat evolved alongside its hosts, and the relationship was one of tolerable low-impact parasitism. The hosts, for their part, evolved behavioral countermeasures, light sleep, skin-twitching reflexes and grooming behaviors that place some selection pressure on the bat to become ever more subtle and precise in its approach. In terms of nutrient cycling, the bat's waste, the dilute urine it excretes in quantity, and the guano it deposits at the roost, contributes to the fertility of the caves and forest floors it inhabits. Bat caves are famously rich ecosystems in their own right, supporting diverse communities of invertebrates, fungi and microorganisms that depend on the accumulated guano of the colony. Vampire bat colonies contribute to this ecological richness in the same way as insectivorous bat colonies, simply with a different nutritional signature to their excretions. The bat also serves as prey for a range of predators. Owls, particularly barn owls and large strigid owls, are significant predators of foraging vampire bats. Snakes access roosts and take bats roosting in hollow trees. Hawks occasionally take bats departing or returning to the roost in the low light of dawn and dusk. The bat thus forms part of the dietary base for a range of aerial and arboreal predators. Its most significant ecosystem interaction, though, is its role in disease ecology. The vampire bat is a reservoir host for rabies virus, and this relationship between bat, virus, and the broader mammalian community is one of the most ecologically consequential relationships in the tropical Americas. Rabies circulates within vampire bat colonies at varying prevalence levels, and while the bats themselves can die from infection, they also exhibit unusual immunological tolerance to the virus, with some individuals appearing to survive infection and others carrying the virus without symptomatic disease. The mechanisms behind this tolerance are not fully understood, but they have made the vampire bat a focus of intense virology research. The bat transmits rabies to cattle, horses, and occasionally to humans through its bite, and this is the primary driver of the persecution it faces across its range. In Brazil alone, tens of thousands of cattle die from bat-transmitted rabies annually, representing significant economic losses to rural farming communities. The public health implications for humans, while real, are considerably more limited than popular perception suggests. Human deaths from vampire bat-transmitted rabies are relatively rare and largely preventable through vaccination. But the fear this relationship generates has real consequences for bat populations, which we will return to. There's also an emerging appreciation for the vampire bat's indirect role in shaping large mammal behavior across its range. Prey animals that co-evolved with the bat show particular vigilance behaviors during the hours of deepest darkness. Some researchers have proposed that the bat's feeding behavior, operating over millions of years, has contributed to the selection of thick-skinned, dense furred body regions in large mammals as protective adaptations, though this remains speculative and is difficult to disentangle from other selective pressures. Part 6. Human Connection and Conservation. The history of the relationship between humans and vampire bats is a story of escalating conflict driven largely by misunderstanding and ecological disruption. For indigenous peoples of the Americas, the vampire bat was part of the natural world, incorporated into mythology, art and cosmology, but not generally regarded as something to be eradicated. The Mayan bat deity Camazotz, the death bat, the night flyer, was a figure of genuine cultural power and ambivalence, reflecting the bat's perceived connection to darkness and the underworld, but also to blood and the vitality it carried. These symbolic associations spoke to a people living close enough to nature to understand that blood was life, and that the creatures of the night were part of the same ecological tapestry as everything else. The arrival of European colonists brought an abrupt change. Cattle, horses, and pigs were introduced in vast numbers, creating an unintended subsidy for vampire bat populations. Where the bats had previously survived on scattered, wary wild mammals, they now had access to dense concentrations of large, slow-moving domesticated hosts that showed none of the defensive behaviours shaped by evolutionary history with bats. Vampire bat populations near ranching areas expanded dramatically. Livestock rabies became a significant economic problem, and the bats, creatures that had been quietly and sustainably feeding in these forests for millions of years, suddenly became, in the eyes of European-derived agricultural culture, vermin to be eliminated. For several centuries, the primary method of control was straightforward extermination. Bat roosts were dynamited, burned, or smoked out. Poison was applied to the entrance of caves. Culling programs were carried out across enormous swaths of Latin America, often targeting not just vampire bats, but every bat species in the vicinity. A spectacularly indiscriminate approach that decimated populations of fruit bats, insect-eating bats, and nectar feeders that were providing essential ecological services entirely unrelated to the vampire bat problem. The biodiversity cost was immense, and the vampire bat problem was never meaningfully solved, because vampire bat populations recover quickly thanks to their relatively high reproductive output relative to body size. The 20th century brought more targeted approaches. The most effective modern method of vampire bat control is anticoagulant paste, applied to captured or encountered bats before release. Vampire bats are extremely attentive social groomers. They groom themselves and their colony mates regularly and persistently. A bat returning to the roost with anticoagulant paste on its fur will spread it throughout the colony through mutual grooming, causing fatal internal bleeding in a high proportion of colony members over the following days. This approach is far more targeted than wholesale roost destruction, as it primarily affects the colony being treated rather than every bat in the landscape. Even this method, however, has serious limitations and unintended consequences. Vampire bat populations in treated areas recover within a few years as bats from neighbouring, untreated colonies expand into the vacated territory. The constant turnover of colony members may actually increase rabies transmission in some cases, as newly arrived bats are more likely to be infected. And the anticoagulant approach still causes significant non-target mortality when applied carelessly. There is growing recognition among wildlife managers that vampire bat culling is not a long-term solution to the rabies problem, and that human and livestock vaccination, particularly oral bait vaccines for cattle, represents a far more effective approach. The conservation status of the common vampire bat is currently listed as least concern by the IUCN, and its populations remain broadly stable across most of its range. In this sense, it is one of the success stories of bat conservation, or more accurately, a species resilient enough to survive despite considerable human antagonism. But this relative security masks important local and regional declines. In areas of intense agricultural development, habitat loss is reducing the cave and tree hollow availability that the bat depends on for roosting. Indiscriminate culling continues in many areas, affecting not just vampire bats but entire cave ecosystems, and climate change is beginning to alter the bat's range in complex ways, shifting the distribution of its host species, altering the rainfall patterns that affect foraging success, and changing the thermal environment of roost sites. The vampire bat has also become a surprising subject of medical research that has generated real value for human medicine. Desmotes, that anticoagulant compound in the bat's saliva, entered clinical trials as a potential treatment for ischemic stroke, where its ability to dissolve clots with high specificity and relatively low bleeding risk made it an attractive candidate. While the trials have produced mixed results and the compound has not yet achieved clinical approval, the underlying research has deepened understanding of coagulation biology and generated new pharmaceutical targets. It is a striking irony. An animal persecuted for causing bleeding disorders in livestock may yet provide the tools to prevent fatal blood clots in humans. The social behavior of the vampire bat has similarly attracted attention from researchers studying the evolution of cooperation, reciprocity, and altruism. The food-sharing networks of vampire bat colonies have become a model system for understanding how and why cooperation evolves in non-human animals. Gerald Wilkinson's landmark studies in the 1980s established the empirical foundation for this work, demonstrating that food sharing in these colonies fits the theoretical predictions of reciprocal altruism with a precision rare in behavioral ecology. More recent work using molecular tools, long-term behavioral tracking, and experimental manipulation has deepened this picture enormously, revealing a social intelligence that routinely surprises even experienced researchers. There is something important in this. Animals that we fear and persecute almost always turn out, on closer examination, to be far more complex and far more interesting than our fear allows us to see. The vampire bat is not a symbol of death or evil. It is not a monster. It is a small mammal, weighing perhaps 30 grams, that has solved the problem of survival in tropical forests in an almost implausibly elegant way. Through a combination of anatomical precision, physiological innovation, and social sophistication that took 60 million years to arrive at. Killing it without understanding it has cost us enormously, not just in ecological terms, but in the irreplaceable knowledge it carries about the nature of cooperation, the mechanisms of coagulation, the structure of disease ecology, and the endless creativity of natural selection. Part 7. My final thoughts. Go back to that Costa Rican cattle ranch. Go back to that cow, still sleeping in the open field, still dreaming whatever cows dream. The bat is gone now, back in the darkness of its roost, hanging from the ceiling with 100 others, its belly warm with blood. In an hour or two it will offer some of that warmth to a hungry neighbour, and in doing so will buy itself a debt that will be repaid on some future desperate night when its own luck has failed. Consider what we've learned. A creature that evolved its way into blood feeding through the side door of parasite hunting, arriving at its present state not in a single dramatic leap, but through the patient, relentless, unplanned logic of natural selection working across tens of millions of years. A creature whose anatomy, the razor teeth, the infrared nose, the anticoagulant saliva, the extraordinary kidney, the improbable walking gait, represents one of the most tightly integrated packages of specialization in the mammal world, every feature precisely fitted to the demands of a single, impossible diet. A creature whose social life has organized itself around the reality of starvation, around the fact that any individual on any given night might return home empty-handed, and has built, in response, a network of reciprocal generosity that is one of the clearest examples of cooperative behavior ever documented in a non-human animal. We learn that the vampire bat's reputation as a creature of darkness and dread is almost entirely a cultural artifact, a product of the entanglement of European vampire mythology with South American natural history, reinforced by centuries of agricultural conflict that began when humans introduced thousands of cattle into ecosystems that had no evolutionary preparation for their presence. The bat simply responded to an opportunity, the way evolution always does. The crisis was ours. The bat was being a bat. We learned that this animal is, in its quiet way, medically, ecologically, and intellectually valuable, that its saliva may one day save stroke patients, that its social networks illuminate the evolutionary foundations of cooperation, that its role in rabies ecology is irreplaceable for understanding how viruses move through mammalian communities. We learned that the extermination campaigns waged against it for a century have been largely futile, occasionally catastrophic for non-target species, and almost always founded on a misunderstanding of both the bat and the disease it carries. And we learned, though this is perhaps the most important thing, the thing that underlies all of it, that the vampire bat is not separate from the world we live in. It is not a parasite on creation, something that the ecosystem would be better off without. It is woven into the fabric of tropical America in ways that took millions of years to construct and that we are only beginning to understand. Its roost contributes to the fertility of cave floors. Its foraging shapes the behavior of large mammals. Its virus circulates through the community of warm-blooded animals in complex ways that are only partially mapped. Remove it, which we've been trying to do for centuries, and which has never succeeded. And the web adjusts, but not always in the ways we would want. There is a bat right now, somewhere in a tropical forest, or on the edge of a cattle ranch in Brazil or Mexico or Colombia, making its nightly rounds. It is navigating by sound, feeling the warmth of living blood beneath its nose, making the tiny, precise cut that keeps it alive. Its ancestors made the same move 60 million years ago. 60 million years of unbroken nights, an unbroken chain of small dark bodies moving through warm darkness, finding blood, returning to the roost, sharing what they have found with those they love. In the dark, against the sounds of a sleeping world, there is something almost tender about it. That is the vampire bat. Not a monster, not a symbol, an animal. And like all animals, examined closely enough, something close to a miracle. If you enjoyed this episode of Animal Uncovered, following the podcast is the best way to support the show. And if there's an animal you want us to uncover next, leave a review or comment and let us know. Until next time.